What's going on, everybody? It's Mr. Gustin back in the physics classroom. Today, we are looking at a race. We're going to have a race in class today. We've been discussing rotational inertia, objects rolling up ramps, object rolling down ramps, how torques produce an angular acceleration. We track that with Newton's second law of rotation, torque equals I alpha. And today is a day we are going to have a race. We're going to race some objects down the ramp. We're going to try to figure out which objects beat other objects. Today is going to be some conceptual understanding, practice, and discussion. So I've got a bunch of objects here today that I found in the classroom. Got a wooden disc. Obviously, these are only physics classroom materials. Like, who has these things lying around? I've got myself a little disc snowman right here. I've got a giant, that's solid, smaller solid sphere, and then inside here, if I can keep these spheres from rolling around, I also got discs. I've got these kind of discs right here. I've got small hoops, hollow hoops, large hollow hoops, and even larger hollow hoop, and then my discs. And they all have varying masses, but they all are the same shape. I've got three of the thin hoops, 3 of the solid discs, and 2 of the spheres. I can probably find a third sphere because I think this is smaller than a billiard ball. This is probably larger than a billiard ball. I could probably throw a billiard ball in the mix as well, and we could race those also. But generally speaking, our task here today is this. We are trying to rank, if I raced all these, if all these raced down a ramp, a flat ramp, at some small angle that prevented them all from sliding, all these things rolled down a ramp, I want you to predict which ones would win in a race down the ramp. Okay, that's the kind of the goal. I want to come up with a list of who wins, who loses, and why. That is the goal here. So take a minute, pause the video, go ahead and take a guess. If I race these things down the ramp, let's go ahead and rank them from small ball to larger ball to small hoop to medium hoop to large hoop and small disc, medium disc, big disc. Rank them. What do you think? Pause the video, think through it. I'm going to go ahead and set some things up on the whiteboard. You think about which of these objects will win in a race. Where's my ramp? There's my ramp. Take 2 minutes. Rank them for me. I've got the big ball. I have small ball. I have small disc, medium disc, large disc, small hoop, medium hoop, and large hoop. There are 1, 2, 3, 4, 5, 6, 7, 8 objects. We'll put a rank right next to them. All right? So first things first, we're going to do this thing kind of heats because, quite frankly, kids, I don't have enough hands to grab them all. So I'm going to do this in heats. All right? First, we're going to start with some of the objects that have similar radii. So we'll do the large ball, the hoop, and the solid disc. We'll do all 3 of these first. We'll race them. We'll see which one wins and which one loses. Come join me on the floor. Come on down here. All right, here we are. I could probably even do the basketball if I wanted to, but we've done the basketball before. All right, and I've got my meter stick here to help me keep things from leaving the track too soon. Let's go ahead and put my meter stick up. Like I said, this is hard. With not many hands, this is challenging. It'd be so much easier if I had like 3 hands. All right, here we go. Ball, hoop, disc. Make sure we can see all 3. Hopefully you can like see through the hoop. Maybe I'll do this. That way you can see the blue ball a little bit easier. It's actually bending my meter stick. All right, ready? I don't know if this is going to work. The ball's rolling towards me. 3, 2, 1, go! All right, well, the blue ball and the hoop was obviously dead last. The blue ball and the disc were kind of tied. So let's try those 2 again. Disc, blue ball. Let's try those again. It was hard to see. Let's do those again. Ready? I gotta make sure that they're kind of starting the same spot. 3, 2, 1, and go. Wow, maybe this meter stick is not doing it well, but again, they're pretty darn close to being tied. Let's see it one more time. If I can just drop them together simultaneously. 3, 2, 1, and go. Well, when I do it like that, when I back them up to the appropriate spot, it's pretty obvious. When I do it with my hand, 3, 2, 1, go. Yeah, when I do it like that, the blue ball wins. All right, so based on like this right now, the blue ball wins. Okay, got it. Blue ball wins. Let's see who wins. I guess let's do it now based on slowest, which was the hoop. Let's do it. Let's see how the hoops compare. Let's see how I have 3 hoops. 1, 2, 3 hoops. Let's see how the hoops compare as we race them against each other. So obviously, varying shapes that have similar radii. Varying shapes with similar radii, it appears that the shape dictates it, right? They've got the same radius, different masses, I guess, but the sphere wins. The hoop loses, the disc is in second, and then the thin hoop, the solid sphere wins, the disc is in the middle. Let's check this one out. I got 3 discs now. 3 discs. I'll put the littlest one nearest you so you can see that. This guy's going over here. Where's my meter stick? My not very good meter stick that is supposed to hold this thing in place. Oh, it rolls right over. That's kind of crazy, actually. It's an interesting concept of center of mass. But so when I do it like this, I don't actually know if they're working so well, but try to raise this up. Back it up a little bit. There we go. All right, see that? Yeah, it's not exactly going to work. Let's see here. 3, 2, 1. I gotta make sure they touch all kind of the same spot is the key here. Let's see if this works. Go! Oh, that's cool. That's pretty cool. Let's try it again. It didn't, because last time we tried it a few different times with the various objects. I'll try with my hands. I'll try and drop with my hands. We'll do little hoop, big hoop. 3, 2, 1, and go. That's like the same time. Little hoop, medium hoop, and if I do big hoop, medium hoop, drop them at the same time, they get the ground at about the same time. So that's kind of neat, right? Like, it doesn't matter. So yes, the hoop loses in the race, but then the hoop also like ties. The hoops are all tied. They are all last in the race, and they tie. So no matter if I use a small hoop, medium hoop, or big hoop, in that first race with the different shapes, like the hoops are gonna lose. So if I have 8 objects, these are tied. Like the hoops, these are all last. Tied for last. Call it 5th place, call it 8th place. They're last. Hoops are last. Let's go ahead and try discs now. Let's see if discs matter. Maybe like, do the discs have something going on different? Let's check that out. Let's see how discs work. Discs are like hoops, but their mass is more evenly distributed. Let's check this one out. Back this guy up, back this guy up. I can drop 1, 2, and 3. Ooh, balance out. 3, 2, 1, go. Oh, I dropped that way too soon. 3, 2. Oh, try to do this with my hands. This is when I need a volunteer. 3, 2, 1, go. I mean, that looks really similar to what we saw for the hoops. And we can drop it a million times over again. But for the most part, we're going to get the same data. Hoops are all kind of tied. Hoops are tied. Discs are tied. That's weird. Something's going on here. So these are last. These discs are, I guess, middle. And so then these are first, big ball, small ball. Let's test it, predict. What do you think is going to happen? Do you think the big ball is going to beat the small ball? Maybe we've done enough data here where you're like, dude, you don't need to drop these. I get the point you're trying to make. The shape matters, not the radius of the object. Well, let's stinking prove it then, right? Like, here we go. I think we proved it. I think we did it, folks. I think we did it. These are first. The small ball, big ball. These are first. It's not a matter of who's better. It's a matter of shape. It's a matter of shape. So now we have this little conceptual conundrum. If I look over here at my data, there's a tie between the hoops, the discs, and the small and big balls. So this is a conundrum. I need to figure out or explain why this is the case. And when I think about this, I go two ways. Number one, I think about what force is accelerating these things down the ramp. If I'm going to win a race, in order to win a race, I need to have an object that accelerates, like to win something must accelerate quickest. Now, this is a general statement, right? There's going to be people out there that talk about weird shapes and weird patterns. And I'm sure Mythbusters has done something to be like, actually, that's not true. Like, yeah, fine. There's a lot of unique motions. But for something that's going in a line, down a ramp, in a sprint-type race, this, generally speaking, is true. And in this race, this is true. The object that wins this race accelerates the fastest. It gets to its top speed the quickest. The force that accelerates these things down the ramp is gravity. And we know that gravity acts on all objects very similarly. It accelerates all objects similarly. So the mass and radius of this thing doesn't matter. The point is there's also a resistive friction force. There's a force holding this thing back. And these objects all have various rotational inertia, meaning these objects don't necessarily want to roll all in the same way. Objects might have higher inertia. They're going to accelerate a little bit slower because they have a larger resistance to that motion. So let's do something. Let's go ahead and figure out what are these rotational inertias for the balls, the discs, and the hoops. I know for the hoop, I for hoop is equal to mr squared, or 1 mr squared. This is what the hoop's rotational inertia is about its axis. For the disk, its I value is equal to 1/2 mr squared, exactly half the hoop. So for objects that have the same radius and the same mass, disks have half the rotational inertia. And then when I go ahead over here to the big ball, small ball, these are solid objects. They're not hollow objects. I gotta make sure I get this right. Solid objects, I believe, are 2/5 mr squared, but I want to make sure that they are before I go ahead and write it down. I was right. Solid objects, solid spheres, I of the sphere is 2/5 mr squared. So, based on this, I should be able to say to myself, for objects that have the same mass and same radius, the sphere is going to have far less rotational inertia. That coefficient kind of dictates that for me. That doesn't explain why objects of different sizes and masses accelerate at different rates, right? If I've got a smaller sphere, a medium sphere, and a larger sphere, or a small disk, medium disk, large disk, they should have the same I equation, so shouldn't the smaller one accelerate faster? It's got a, well, I guess it has a smaller radius, which tends to matter more, right? Like, this is confusing to me, so I got to dive into this further. But I understand that shape dictates I, or rotational inertia, so shape matters. Let's look at what produces the acceleration. I've got two things, right? I've got my F net equation, which is m times a. The force that pulls it down is mg sine theta. The force that holds it up is the force of friction. That's what this is. It's what holds it up. What causes it to rotate is the net torque. Net torque is I times alpha. It's also equal to the force of friction times R. This is also true. So I see force of friction showing up in both places. For an object, say a hoop, I would say that 1/2 mr squared times alpha is equal to the force of friction times R. This is also a way to write this. I'm trying to figure out, why does mass and radius not matter in this thing, in this race? Well, if I'm thinking about linear acceleration, something accelerates to win. If I'm thinking about linear acceleration, my mathematical equation becomes this. A over R. I use a bridge equation to get from alpha into linear acceleration so I can figure out how fast that center of mass is moving down the incline. This is still force of friction times radius. What I'm noticing is that this radius goes away. This radius quantity goes away. And all I'm left with is 1/2 ma is equal to the force of friction over here. Okay, so force of friction is dictated by the mass of an object? Well, yeah, definitely, because like heavier things have more friction. They stick together as a larger normal force. We know that to be true. But does that mean that mass impacts acceleration? Well, let's check this back out right here. When I plug this back in to actually calculate what is my linear acceleration, I find that ma is equal to mg sine theta minus 1/2 ma from force of friction. Check this out, folks. The masses all fall out. And what I'm left with, I add this over, I get like 3/2 a. If I add that there, 3/2 a is equal to g sine theta, and a is going to be 2/3 g sine theta equals a. This is what I'm left with. Is that important? That's not necessarily as important as understanding what causes acceleration. Gravity. And like we learned way back when we were out at the bleachers dropping objects from different heights, is that gravity accelerates all objects at the same rate when they take the same path. A great example is free fall. The only difference here is that these objects are not freely falling. There's a resistive force, and that resistive force is friction. And these objects don't just have linear motion, they're also overcoming this rotational inertia. And so objects that have different rotational inertia are going to resist or begin rotating easier or harder based on their distribution of mass. The big takeaway here is that objects that are going to win a rolling race need to have the smallest rotational inertia. If they have varying masses and radii, it doesn't matter. Gravity is still the accelerating force. If they have different shapes, however, we need to overcome the various rotational inertias of the objects in order for it to win. These are the takeaways. I hope this isn't too confusing. The moral of the story is that shape dictates linear acceleration when objects roll. That is the big takeaway. Here's a mathematical explanation. Here is some data over here along with our I values to hopefully let you see the differences in rotational inertia. If you've got questions, drop in the comments. Heck, if I messed up, drop in the comments. Send me an email or ask me in class. Until next time, see ya!